Hi everyone, I'm Ryan Wu from the University of Chicago. In the next few minutes, I will introduce our work on triple ion quantum computing research. And this work is collaborated with Duke University and Argonne National Lab. Triple ion is a promising technology for building scalable quantum computing systems. And in a triple ion system, an ion is the physical expression of a qubit, and each ion can be physically shuttled over the trap surfaces. In the current triple ion devices, QCCD is a proposed model to scale triple ion quantum computing systems. And this device requires complex junction shuttles and trip design as they scale up. In addition, QCCD requires ion chain split merge operations during the process of computation for communication with qubits in different traps. However, merge and split operations are difficult operations comparing to just shuttling. In this work, we evaluate another architecture, which is tripped ion linear tap architecture. In short, we call it tilt architecture. And in tilt architecture, we have multiple qubits. Here we say we have n qubit in an ion chain, and the quantum gates are implemented through laser-based operation. And we have L laser controls, and n is greater than L. So we use the laser heads to form an execution zone in the middle of the trap. But we can actually shuttling the entire linear chain together back and forth so that we can still operate on all the ions, even if we only have a few laser heads. So tilt architecture will act just like a Turing machine. This ion chains form like a tap, and this tap moves back and forth during the execution. As for our key contribution, in this work, we present a comprehensive design and evaluation of tilt architecture, and we hope our evaluation can inspire more experiments to do more physics experiment in this direction. And to evaluate the performance of tilt architecture, we develop our tool flow. Also, we simulate using a noise model extracted from realistic experimental studies to estimate the application reliability. This is an example of tap movement. Assuming we have a single qubit gate on the blue qubit and the green qubit, to complete two operations, we firstly shuttle the entire tap to the right until the blue qubit is in the execution zone. And in order to operate on the green qubit, we will have to shuttle the entire tap to the other direction so that we can put this green qubit in the execution zone, and then we can apply our gate on this qubit. Because start and the stop of the tap shuffling will add thermal to the system, and hence these operations will cause noise to the system. Our goal here is to minimize the number of tap moves. For a 2-qubit gate, if the distance between the pair of qubits is longer than the execution zone, we need to add swap gates. For example, if we have a 2-qubit gate on two blue qubits, then we have to first swap this blue qubit with a green qubit. And in the next step, we swap this blue qubit with the yellow qubit. Finally, until two blue qubits are in the same execution zone, then we can apply this 2-qubit gate on them. And the goal of the swap insertion is to minimize the number of swaps. And compare tilt with QCCD, considering we have four 2-qubit gates, G1, G2, G3, and G4, and you can see if they are short distance 2-qubit gates. For QCCD, we need 4 swap split shuttle, and merge operations to complete all four gates. However, in the tilt architecture, all we need is simply a tag move. So the takeaway here is tilt architecture can perform better than QCCD if your circuit contains multiple short distance 2 qubit gates. We compare different sizes of tap head size. The head size of 32 is much better than 16 in terms of success rate because we can reduce the number of swap and moves with larger execution zone. Comparing to prior work in QCCD evaluation, 32 head size is better than QCCD for those benchmarks with short distance 2 qubit gates. To conclude, tilt architectures offer a viable path toward QC devices approaching 60 qubits, and we present our optimizing compiler and the simulator for tilt architectures. The results suggest that tilt can outperform QCCD in a range of NISQ applications. There are more details about our study and the future work in the paper. If you are interested in this line of research, please refer to our paper. Thank you.